There is a bruise on the sky. If you photograph the entire universe, not the stars, not the galaxies, but the oldest light that exists, the glow left over from the Big Bang itself, you get a map, and that map is almost perfectly smooth. Almost. Because in the direction of the constellation Eridanus, there's a patch that's wrong. A region roughly 3.5 billion light years across where the light is colder than it has any right to be. Not slightly colder. Across the rest of that map, temperatures wander by about 0.02 of a degree. This patch is off by 0.15, 7 times the normal deviation, spread over a region so large that our entire galaxy would be a speck inside it. Astronomers have spent 20 years trying to explain it. They found something, and what they found only made it worse. Because whatever they discovered out there accounts for, at most, 20% of the problem. The other 80% has no explanation. And one of the ideas on the table is that we are looking at the scar left behind when our universe collided with another one. To understand why this is strange, you need to understand what you're actually looking at. Rewind the universe. Not thousands of years, hundreds of thousands. In the beginning, everything was so hot and so dense that atoms couldn't hold together. Electrons flew free, and in a universe full of free electrons, light can't travel. Photons scattered constantly, like headlights in fog. The universe was opaque. Then, about 380,000 years after the Big Bang, it cooled just enough. Electrons finally locked into orbit around nuclei, the fog cleared, and in that instant, light was released in every direction at once. That light is still traveling. It's been stretched by the expansion of space from a searing glow into faint microwaves, and it's arriving at Earth right now, from every direction in the sky. We call it the cosmic microwave background. It is, quite literally, the oldest thing you can see, a photograph of the universe as an infant. And here's what makes it the most powerful tool in cosmology. It's almost perfectly uniform. Point a detector anywhere in the sky, and the temperature comes back at about 2.725 Kelvin. Everywhere, in every direction. Almost. Because the tiny variations, those hundredths of a degree, are the seeds. Slightly denser patches in that infant universe became the places where gravity pulled matter together. Every galaxy, every star, every planet, every person grew out of those microscopic ripples. So when we look at the CMB, we're not just looking at old light, we're looking at the blueprint, and cosmologists have gotten extraordinarily good at predicting exactly what that blueprint should look like, which is how they noticed that one part of it doesn't fit. The cold spot didn't announce itself. It emerged from statistics. When the first high-resolution CMB maps came in, researchers ran the data through tests designed to find anything that deviated from the expected pattern of random fluctuations. In the southern sky, in the direction of Eridanus, one region kept flagging. It was too cold, too large, and too well-defined to sit comfortably inside the predictions. Now, I want to be careful here, because this is exactly where a lot of channels overstate things. Statistical anomalies in enormous datasets are not automatically profound. If you search a big enough map for unusual features, you will find unusual features. That's not mysticism, that's arithmetic. Cosmologists have a name for this trap, the look elsewhere effect. So the honest question was never, is there a cold patch? The honest question was, is this patch cold enough and big enough that random chance becomes an uncomfortable explanation? And after 2 decades of better instruments and better analysis, the cold spot has not gone away. It has survived independent measurements from different satellites using different detectors with different systematic errors. It is not an artifact of one telescope having a bad day. Something is there. The most elegant explanation didn't require new physics at all. It required a hole. Here's the idea. As that ancient light travels toward us for billions of years, it doesn't pass through empty nothingness. It crosses the structure of the universe, clusters, filaments, and the vast underdense regions between them. And here's the key. Our universe's expansion is accelerating, driven by dark energy. That acceleration does something subtle to gravity wells. When a photon falls into a large void, a region with less matter than average, it gains a little energy on the way in, like a ball rolling downhill. Then it has to climb back out, losing energy. In a static universe, those two effects would cancel perfectly. But the universe isn't static. While that photon is crossing the void, dark energy is stretching the void even wider. So the hill it has to climb. They went and looked, and they found it. Surveys counting galaxies in the direction of the cold spot turned up a genuine underdensity, a supervoid in the constellation Eridanus at relatively modest distance. It's not a rumor or a marginal detection. It's been supported by galaxy counts across multiple surveys, by reconstructions of how galaxies are moving, and by weak gravitational lensing analysis from the Dark Energy Survey team. The Eridanus supervoid is real. It is enormous, and it sits exactly where the theory said it should. This should have been the end of the story. Mystery identified, mechanism confirmed, case closed. Except when they did the arithmetic, the numbers didn't work. Under the standard model of cosmology, the same model that successfully predicts almost everything else about the CMB, that supervoid can only account for something like 10 to 20% of the temperature drop we actually observe. Read that again because it's the whole video. They found the suspect confirmed, and the suspect is responsible for a fifth of the crime. So now the situation is worse than before. Before, we had an unexplained cold patch. Now we have an unexplained cold patch and a confirmed void that isn't big enough to have caused it. The obvious answer turned out to be a partial answer. And partial answers are the most uncomfortable kind, because they prove you were looking in the right place while telling you you're still missing something. Which brings us to the idea that gets all the attention. The proposal is this. What if the cold spot is not something inside our universe at all? What if it's a mark left on our universe by contact with another one? I need to frame this properly, because the phrase a parallel universe does a lot of unearned work in popular science. The multiverse in this context isn't a fantasy about alternate versions of you. It comes out of eternal inflation, a mainstream extension of the inflationary theory that already explains several features of our universe very well. In that picture, the rapid expansion that inflated our cosmos never fully stopped everywhere. It continues, and pockets of it stop locally, each pocket becoming its own bubble universe. If that's what reality looks like, then bubbles can, in principle, touch. And a collision between two bubble universes early in their history would leave something behind. A circular imprint on the cosmic microwave background. A bruise. That's the hypothesis. Not a portal, not a doorway. A scar in the oldest light we can see. Now here's the part that matters, and it's the reason I wanted to make this video. An idea like we collided with another universe is only worth anything if it can be proven wrong. Otherwise it's a story, and this one can. In 2017, the astronomer Tom Shanks pointed out the specific test. A collision between bubble universes wouldn't just leave a temperature signature, it would leave a distinctive polarization signature in the light of the cold spot. Polarization is the orientation of light waves. The CMB carries polarization patterns that encode information about what that light passed through and how it was scattered. Different physical causes leave different polarization fingerprints. An ISW effect from a void leaves one pattern. A primordial collision would leave another. So the multiverse hypothesis isn't unfalsifiable hand-waving. It makes a concrete prediction about a measurable quantity, and future high-precision polarization measurements of that region can support it or kill it. That's the difference between speculation and science. Not whether an idea sounds outlandish. Plenty of accepted physics sounds outlandish. The difference is whether the idea sticks its neck out. And as of right now, that measurement has not delivered a confirmation. There is no evidence that a collision happened. What exists is a hypothesis with a defined test that hasn't been passed. I don't want to leave you with the impression that it's either a big void or another universe. There's more on the table, and honestly, the boring options are still the favorites. One possibility is that the supervoid explanation is right, but our modeling is incomplete. Maybe the void is more elongated along our line of sight than we can measure. Maybe several aligned underdensities are stacking their effects. Maybe the way we calculate the ISW contribution needs a refinement. Another possibility is that it really is a statistical fluke, a rare but not impossible fluctuation that we fixated on precisely because we noticed it. And a third possibility is the most interesting to physicists but the least dramatic to describe, that the cold spot is one symptom of a larger problem with the standard model of cosmology. Because the cold spot isn't the only thing that doesn't fit. There's the Hubble tension, two independent ways of measuring the universe's expansion rate that stubbornly disagree. There are other large-scale alignments in the CMB that shouldn't be there. Individually, each one is a curiosity. Together, they form a pattern of small cracks in a model that otherwise works beautifully. Sometimes a set of small anomalies is just noise. And sometimes it's the first sign that a theory is about to be replaced. So let me be direct about where this stands, because you deserve the real answer, rather than the exciting one. Is the cold spot proof of another universe? No. There is no evidence of a bubble collision. The polarization test that would support it has not come back positive. Is the cold spot explained? Also no. We found a genuine supervoid in exactly the right place, and it covers a fraction of the effect. The majority of that temperature drop remains unaccounted for. What we have is a confirmed anomaly with a partial explanation and a falsifiable long-shot hypothesis attached to it. That's not a disappointing answer. That's the most honest description of an open problem in modern cosmology. And I think there's something worth sitting with here. We built instruments capable of measuring the temperature of the entire sky to within 100,000th of a degree. We used them to photograph the universe as it existed before there were stars. And in that photograph, we found a mark we cannot account for. Whatever made it happened either in a region so vast it dwarfs everything we know, or before our universe was even finished forming. Somewhere in the direction of Eridanus, the oldest light in existence is carrying a message we haven't learned to read. Which explanation do you think it turns out to be? A void we've mismeasured, a fluke we've overinterpreted, or a bruise from something outside? Tell me in the comments. And if you haven't seen it, watch the video on your screen about the Boötes void, because that mystery and this one might turn out to be the same story. See you on the bright side.